Okay, I'll just unmute myself. Thank you, everyone. I'm having a little issue with my internet connection, so if there's any problems, please let me know and I can repeat myself. But I'm Mark Blackford. I'm the current director of Variable Stars South, and I welcome you all to this much delayed 6th edition of our Variable Stars South Symposium. It was originally planned for 2020 at the Parks NACA meeting, but of course some little bug got in the way. But we've finally managed to put it together as a virtual meeting, so hopefully this all goes smoothly. There's been a few teething issues this morning, but we're getting there. Hopefully our 7th symposium in a couple of years' time can be an in-person meeting and we can actually interact properly. Firstly, I'd like to thank David O'Driscoll for his technical expertise in running this Zoom meeting. His input has been invaluable. It probably wouldn't have got off the ground at all without him, so thank you, David. David, if you could put up the program of our speakers over the next 3 weeks, that'd be great. Okay, so we have quite a good lineup, an excellent lineup of speakers and topics over the next 3 weekends, starting today with our professional colleague Ed Budding. We've had a few last-minute changes to the program due to COVID isolation and unavailability for scheduling problems, but we've got through that. So the current lineup of our talks is as shown on the screen now. With today we have Ed Budding, Stan Walker, Royal Axelson, and myself closing out the proceedings. Next Saturday, Arne Hendon will be our first speaker, followed by Tom Love giving two talks on various aspects of spectroscopy. And we'll finish up with David Moriarty on another spectroscopic / photometric talk. On the following Sunday, the 2nd of October, we have 5 talks lined up with Carl, Leah Bernabo, who is a PhD student over in Germany. She's Italian by origin, but studying in Germany. Stan Walker will speak again, as will Arnie to finish to finish the program. But before then, Jeff Byron will give us an update on his technique for determining times of minimum from light curves. So that's the program as it stands at the moment. We'll see if that stays that way for the rest of the symposium. Okay, look, let's get going on our first talk today, and that will be given by Ed Budding, who has been collaborated with Variable Stars South members for many, many years now, and quite a few journal papers have resulted from those. Today, he will present an overview of some of the more recent studies of close binary stars that we've been working on. So, Ed, if you're ready, we will get going.
Right. Well, let's stay with that and see what happens. It's not actually the slideshow, but time's moving on, so let's get into it. I think it's all going to be visible from this type of picture, isn't it? I'd like to echo Mark's kind words at the beginning, directed to David, who's got us off the air this morning with a few knowledgeable interventions, which I very much appreciate. And also, thanks to the audience for turning up, listening to us. Hope it goes well. And these technical methods have their problems, as we've been finding out, but certainly quite a bit cheaper to arrange international gatherings through the internet, and maybe the technology will improve as time goes by. It's something to sort of hope for. So let me crash into this, and the talk will be similar to one that I gave at Sydney, the Sydney NACA meeting that Mark mentioned a few years ago, and therefore you may have seen one or two things before, but hopefully not too much. I'm going to confine attention mainly to the 3 close binaries that our group published papers on in the last year. And if time permits, mention something about a couple of other stars that, well, in particular, Stan Walker's drawn attention to. We'll see how the time goes. So this slide, the first one, shows some of the related facilities to the Southern Binary Program, as we call it. New here are tests at the bottom left there, and a micrometer attaching to the back of a telescope, which I'll say more about later. It's a relatively new device in some ways. In some other ways, it's an old device for astronomers. Okay, let's see if that works. You've got a view of the model of part of the galaxy here. Everyone see it okay?
Yeah, it's fine, Ed.
Yeah, okay. So this is the Gould Belt, and it's a reminder that binary studies are not just confined to stellar astrophysics, but using the absolute parameters from binary stars, we can connect also with studies of the galaxy and its processes and makeup. And one such process, still not well understood, is the Gould Belt, kind of local large region of star formation involving various so-called young star associations, or OB associations, because of the early type spectra. And interestingly for us, the near and more accessible of these star formation regions are in the sky's southern hemisphere. So it's a bit of an invitation there for us. But ideas are still not settled about this formation. The large circle idea for the belt, for instance, has been questioned in more recent studies, and it may have been superseded by the so-called Ratcliffe wave, which is a long structure of connected star formation regions extending along a galactic spiral arm. The discussion goes on about such matters, but clearly knowledge of basic stellar parameters is going to be of assistance in working out the geometry of this larger scale astronomical feature. But let's get back to our main focus in this. The eclipsing binaries tell us quite a lot about stellar properties, and in particular the usual combination, the so-called Royal Road combination of flux variation and radial velocity variation obtained by photometric means or spectroscopic means. Here also they've got a picture of what the orbits look like in the ZX plane, Z being the direction of the line of sight. And when the inclination of the axis of the orbital plane to the line of sight is low, we might see something like that on the sky, and that's often the case for visual binaries, as they're called. We don't hear too much about those in this context, but I think we're going to hear more about it with high precision astrometry in the coming years. I mean, we need very high resolution to see the orbits of most eclipsing systems. At the present time, somewhat out of range, but this will crop up because many of the stars, the young stars that we look at in this program, appear to be members of multiple star systems, where the outer components are part of astrometric data collecting. So let's get on to the first of our 3 stars, which is Pu Puppis. This is the Hipparchus light curve of a few years ago, the discovery of the variability of the system was made through Hipparchus. And it's showing what at that time was known as an ellipsoidal variation. That is, without eclipses visible, but you know that it's a binary from the shape of that variation and the period. You don't know perhaps for absolute certain. If you can confirm it with spectroscopic means, then, well, you're home and hosed as far as the character of the system is. But see how things change with the TESS era. Look at the accuracy of that light curve. And here we notice something else, that in the bottom of these minima of what we've just taken to be a sort of tidal variation in shape due to tides of the system components, there's something else added here, which is these very small grazing eclipses. And although only slight features of the light curve, they will have a strong influence on the modeling parameters. Okay, a model of the system was constructed using the well-known Wilson-Davini program. And notice here that the primary of the system is very large compared to the secondary, both main sequence stars, but the primary being more massive has evolved faster and now approaching its so-called Roche lobe. And this arrangement of primary and secondary, where you have the primary almost at the Roche lobe when things will start to happen in terms of interaction, is relatively rare. It's usually when we find stars interacting due to Roche lobe mechanics, the primary has already lost more mass than brought it down in mass so much that it's less massive than its companion. If we look at these two stars and look at their absolute parameters, we can match them up with theoretical isochrone, as it's called, variation of the size of the radius, the size of the star with the mass for a given age. And we find that both stars fit on as main sequence stars if this is of the order of 170 million years. So that's the kind of picture we can get of combining theory with these detailed observations and analysis to get a closer picture of stellar parameters in the wild, as it were. Okay, the next star of the trio that we had in mind for the talk is another Puppis star. V Puppis is a rather more well-known object, and it's actually in the interaction stage that we associate with the term Algol type binary. It's also not far, you can see here, from the well-known star Gamma Velorum. And this region here, all around this part of the sky, is rich in star formation regions. In particular, the Gamma Velorum is associated with the central region of the so-called Vela 2 OB2, Vela 2 OB association. So, you know, the getting absolute parameters for stars in these sort of conditions is going to be useful when you put that knowledge together with other knowledge gained from the clustering of the stars to get a deeper insight into physical processes and what's going on. And at this point, it might be useful to recall something you're probably familiar with, but the so-called Algol systems. And this is recalling the so-called dog hypothesis of that picturesque term was introduced by Hoyle, the idea of the one star having expanded and starting to spill over onto the other. I should say that this spilling over of matter from one star to the other doesn't necessarily occur in all systems. And in fact, two main cases of this Roche lobe overflow considered, case A and case B, the more Hoyle-esque dog-eat-dog scenario of one star dumping matter on the other is perhaps more associated with the case B, and rather cooler, less massive systems. V-Puppis, in fact, is a case A situation where the star starts to lose matter from its rush lobe container while it's still on the main sequence. And also, if these are hot enough stars, that matter doesn't actually reach the other star, but is expelled by radiation pressure from, or it can be expelled, this is what we think happens, from the system, and leaving the other star to evolve more or less as a single star. That's an idea that seems to be supported in our results. And also, you can see here a third star. I mentioned a lot of these massive stars are in multiple systems, and that seems to be the case also for V-Puppis. This is a model of the V-Puppis system from our data analysis, and we found it to be a case A type algol. This kind of software freely available, a little bit old-fashioned now, but I still find it handy. This is a diagram, not as good as some of the other models, perhaps not as good as the artist's impression we just saw, but nevertheless true to Rush lobe formulae. Okay, let's press on. I wanted to show the important job done by many amateur observers of timing eclipse minima, because in this way mass transfer and loss can be tracked due to the varying speeds of the two main bodies as they adjust to the changing masses. You will get changes of period and so on, and this process can be monitored by relatively simple equipment. We've got here some observations from Mark for a system comparable to the ones we've been talking about, ETA Muskie. And from the putting together the information about observed minus calculated times of minima, as we shall see a little bit later, we can add to the store of knowledge we have on these interacting binary systems. So enter test photometry again, and we can see what a difference this high accuracy photometry is making to our analysis. In fact, this is an amplified scale of the residuals here, but you can see systematic effects, particularly associated with the partial eclipse regions of the light curve. This, in effect, is telling us that there are aspects to this system that are not really properly taken care of by the modeling we're doing, even though the modeling is fairly accurate, it's plausible, and supported by detailed physical considerations. There's still something else there that that doesn't fit in with that modeling. And in fact, further analysis of that, let me show this because it continues more with, I'll come back to that other slide. The additional effect, you see, when we've been that's what we've been doing with the test data to begin with, it's been all the sequence of eclipses together and do a fitting to that. If you look at individual light curves one by one, you'll see the residuals show this rather smooth pattern of pulsational behavior superposed on the light curve due to the binary effects. This was a discovery we made for V-Puppis, and it shows that the primary star in the system, the one which we think is like a main sequence star still, is oscillating as a beta Cepheid type variable. Let me just quickly go back to the other slide. This is the sort of thing you'll see in papers. You know, these are so-called parameters. Some of them are sort of fixed, like these limb darkening coefficients, or temperatures are fixed from other considerations. But you get some quantities which are actually measured from the light curve analysis itself. Hipparchus gave us these numbers. TESS gave somewhat different numbers for the fractional contributions to the luminosity of the two components, slightly different ratio there, but it's in a different spectral region. TESS operates in the near infrared, and then we can pick out this third light reasonably confidently. So as I pointed out before, many of these early type binaries are in multiple star systems. Okay, regarding the beta Cepheid pulsational behavior of the primary, that shouldn't have been too much of a surprise, because when we put it on this so-called Hertzsprung-Russell type diagram, where we have the temperature on one axis and the luminosity on the other, we find that this primary star is close to the revised instability strip for early type main sequence stars. So this behavior is similar to other B stars of a similar condition. And so perhaps we could have expected that, but at the time, it was just one of these novelty things that take you a bit by surprise. Again, we can use evolutionary diagrams to show how, as time goes by, as the age increases, the star will expand. This is, again, we're still talking about the primary, the more massive, the present primary, the more massive component in the system. And so we're measuring here the size against the size we determined from the observations. And we come out with an age of about 5 million years, which we can take to be an age for the system, the Vela 2 association that I mentioned, given if this system is a member of that association, which we take it to be, because it's the same distance, same direction, and it fits in with the luminosity. So independent checks from binary studies of properties that we'd associate with bigger systems. Okay, the final star in this little review is V410 Puppis, another Puppis star. And these light curves, again from Mark, BVR. You can see that looks like a typical, from the shape of it, like a typical EB type, eclipsing binary light curve, early type system, eclipses of comparable depth. But it's only 5% of the overall light level. So what's going on? Why is it so? Why are these eclipses so shallow? The answer to that, a little bit of thought, can easily be seen to be the presence of some other star or stars in the monitoring. And indeed, there are 4 stars in this system, and the A little a and A little b are the excuse me, 2 stars of the close eclipsing system, the more massive totally, if you add the whole weight of those 2 close components together. That's object A. Object C is at 30 seconds of arc distance on the sky, a relatively bright star, early type, discovered as a visual companion to star A by John Herschel at the beginning of the 19th century. Star B, this may be of local interest to some of our colleagues here today. Star B was discovered later, at the beginning of the 20th century, by Robert Innes at the Sydney Observatory, central Sydney there. And that's very close into star A at a distance on the sky of less than 1 arc second. So one of the jobs that we had to do early on, and Mark helped with this, I think at first his photometer was including all 3 stars, and then he was able to sort of restrict his diaphragm to enable us to separate A and B. So one of the challenges here is to separate these contributions. It's come from a combination of measurements on the sky and analysis of the light curve. And that enables us, when we get the magnitudes and colors sorted out, to work out what the temperatures are going to be, which will be useful parameters to put into the modeling. Again, we saw oscillatory behavior in the residuals Actually, this was noticed first, I think, by Tom Love, who's going to speak the next session of this meeting. He may refer to this. He certainly produced this frequency spectrum. I think he used something called Paranso. Some of you will be familiar with that, I'm sure. And this is just the stuff that astroseismology is made of. They love to handle this kind of data. It's rather a slow period oscillation here, 3 a day. It's an 8-hour period for the main components of the SPB type variation, slow pulsating binary type variation. Picked up again because sort of in the residuals from modeling tests, high quality data. So here I want to sort of get back a little bit to the basic ideas of binary star systems, you know, 2 stars revolving around a common center of mass. But with the visual binaries, you wouldn't sort of do it in that way. You look at star A, the bright one, and you measure how far away the distance is on the sky in arc seconds, usually, to the companion. The orbit of the companion, you can show this with relatively simple maths, is just a scaled up version of the ellipses that both these stars perform about the center of mass. So you're measuring theta, the variation of position angle between the direction to the other star and some fixed direction, and that separation, and you're looking for something like Keplerian ellipses and the parameters of a Keplerian ellipse to tell you something about the physical parameters of the things like the mass of the stars involved. And so this is where I'm going to take my leave for today, because this is kind of a little bit of a new branch showing up, and I think more so in future studies of binaries. We fitted here an ellipse to the observations of the AB system in V410 Puppis as a visual binary, and added that into the MISC. We found that the total mass of the system, I think, if I remember right, was about 10 solar masses. So we could put, we could apportion based on the luminosity ratio what we thought the masses of the various stars would be, and fit it in with an overall scenario for the system with this multiple stars. So if you're interested in binaries, keep in mind that particularly with these young, early, massive type stars that we've been looking at, that they're often in multiple systems, they're near to star formation regions. They're going to tell you a lot about wider branches of astrophysics, which hopefully will whet the appetite, even if it's for just timing minima. You know, it's all contributing to the mix of data, which makes this subject exciting. Okay, thanks for your attention. Now that's enough for me for now. Thanks. Are you still there?
Yes, we're still here.
Oh, okay, I thought everyone had gone to sleep for a moment.
No. Thank you, Ed. That was great. A brief overview of the types of systems you and the rest of your colleagues, including myself, are working on. I might point out that a lot of these stars are really quite bright. I think most of them are probably visible to the naked eye, and that helps with the spectroscopy because the exposure times can be a lot shorter. And there are a lot of very interesting eclipsing binary systems in the Southern Hemisphere that just have not been properly and fully investigated yet. So we have opportunities down here. And these sorts of collaborations with Ed and others give us an opportunity to actually make real contributions to the science. So thank you, Ed, for including us.
You're welcome.
Anyone have questions? And remember to unmute your microphone. Well, perhaps you've stunned them all, Ed.
Sorry about that. Yeah.
Now, I'm actually going to ask a question. I was just waiting for others to get in. Ed, you showed that slide a few slides back where there was what you described as systematic changes as the light curve went through.
This?
No, a bit further back.
Well,
That one there.
Yes.
So
Yeah.
are you saying that in this case of the purpose, we're talking about other components, or were there other types of variation that they were concerned about there?
Well, what I'm referring to here is particularly associated with what we've called or described sometimes between ourselves as a W effect. You can see here this W shape, which crops up in the minima. And we're using, you get a bigger W, in fact, if you only use a linear limb darkening law for the surface. We're talking really about an effect, I think, which becomes concentrated during the times of eclipse and relates to the distribution of brightness across the surface of the star that's being eclipsed. And this is normally, traditionally was done in terms of a so-called law of limb darkening, an effect which you can see on the sun quite directly. To a first approximation, this obeys a relationship to the cosine of the angle of foreshortening, a linear connection. But at finer detail, this sort of breaks down. We've used a quadratic approximation here and reduced the scale of this W effect. We can also reduce it by modeling the penumbral eclipse part of the eclipse with the umbral part of the eclipse in some cases, with separate coefficients. But it seems a bit ad hoc. And what we probably need is a more thorough way of handling the interaction effects, the illumination, the tidal effects, and the basic limb darkening effect, relating to the way the light comes out from the atmosphere of the star. Complicated topics to handle in detail. I don't think we're quite there yet. And what this is showing us is that test data will offer theorists some scope for more detailed models, and in due course that'll mean that will be fed into data analysis programs, I guess.
Yes, it's only recently that TESS and other satellite photometry systems have really pushed the boundaries right down to the point where we can see these effects from the ground. It's all the resolution of the instruments, the precision of the measurements is too coarse to see them. So
yeah, I was just going to say that some remarkable, I mean, this all grew from exoplanet research. The Sagan's little blue dot has been the driving force for a lot of this vastly improved photometry accuracy. You talk routinely of getting mean accuracies of light measurements to, 1 part per million, something like that. Is just unexpectedly, well, to people my age, unbelievable kind of accuracy limits. But to go back to another point you made before, by the way, about bright stars, Mark. Yeah, you're quite right, because here in Aotearoa, we call it, we can only afford a 1 meter telescope to put at the. We have a very good, world-class, I would say, spectrograph at Mt John with the Hercules spectrograph, but still only a 1 meter telescope to use in conjunction with that. So we are a little bit confined to brighter stars if we want to get good time resolution. But there are a lot of them, and as we said right at the beginning, these star formation regions are not, in the southern hemisphere at least, not too far away from the Earth. I mean, 300, 400 parsecs, something like that. And that it means that you'll see early type stars still, as you say, visual objects. You can see them with your own eyeballs.
Okay, unless there are more questions, we might move on to our second presentation.
Yeah, before we do, Mark, just